My name is Mariana, and I work at ECMWF, which is handily, I've got the logo there, but I'm going to, a lot of you might not be familiar with it, so that's going to be part of the talk. And my talk is going to be about whether we can use machine learning methods to replace numerical weather models. And this is a really hot topic of discussion at the moment. Like with anything, with all fields, really, machine learning is sort of taking over. And so, yeah, so this is the question that I'm hoping to answer in this talk, and then we can reach a conclusion at the end, maybe. And so, yeah, I'd like to thank the AIFS team, or a lot of whom have contributed to these slides. And you'll find out about AIFS, what that is exactly right at the end, which is it's our new exciting model. And if you have any questions after the talk, please feel free to email me. My email address is on the screen, but I'm pretty easy to find, I think. So, yeah. Oh. So for the outline, so I'm going to start with who is ECMWF, because, yeah, I guess most of you machine learning background, so you might not know who we are. Then I'm going to talk about what is numerical weather prediction. So that's what we currently use for forecasting. Any forecast that you get on an app or on a website or from the BBC or the Met Office will always be, for the moment, is numerical weather prediction. So what do we mean by numerical weather prediction? Then a little bit about machine learning's role in numerical weather prediction, which I guess will be the most interesting topic for this audience. And then finally, the challenges that come about by using machine learning models in numerical weather prediction, and some ideas of how we might overcome these challenges. So to start off, ECMWF. So we were formed in the late 70s, and we're an intergovernmental organization, and it stands for the European Centre for Medium Range Weather Forecasts. And these countries that you see filled in, those are our sort of member states, if you like, and the flags are all at the bottom of these slides. And the idea of ECMWF is to try and address the critical and most difficult research problems in weather, which no one country on its own could sort of tackle. Purely because the idea is if we pool all our computational resources and financial resources and also personal like staff resources together, then we can really build a very exciting model. And so you can see, so I'm based in Bonn in Germany. We have originally the office was in Reading, and there's the supercomputer where we run all of our simulations is in Bologna, along with some stuff. So we're sort of now multi-site. And what do we actually do? Well, we produce hundreds of weather products specializing in medium range. So that tends to be from sort of 5 to 15 days. So most regional weather centers will not actually produce a forecast past 5 days. They just don't have the computational resources to do it. And so if you see a forecast at 7, 8 days, something like that, it's probably coming from ECMWF, even if it says whatever weather organization at the top. But we also have, obviously, in order to predict 5 to 10 days out, you also have to predict 1 to 5. So we have lots of short range weather products as well. And most relevant really for machine learning is that it's the home of the largest archive of weather data in the world. And that's obviously very, very attractive for machine learning. And because we're a public organization, all of this data and all of these sort of products are freely available. It may not be freely available outside of a member state, but yeah, freely available to everybody in a member state. So, and that's a bit about ECMWF, but what is the sort of bread and butter of ECMWF? What is numerical weather prediction? How do we make a forecast? So the weather system is quite complex, as I'm sure all of you know. So we're trying to predict the future through the observations of the present. And we receive 800 million daily observations, which is a lot of observations. And that's the sort of normal things that you would expect, like temperature and wind and rain and snow and the things that you would need for to predict weather, but also things like trace gases and aerosols, soil moisture, lots and lots and lots of observations. So see if we can try and make a forecast. Next slide is not wanting. Let's try this. And so where do we get these observations? Well, I'm sure you can imagine what a lot of them are. There's lots of sort of sensors nowadays on planes and on ships, and we collect data from them. You also have satellite data, radio sondes, which are just basically these balloons that get launched up into the air, radar, so all sorts of different sources of information. And this is particularly important for the problem is that we don't have just one source. So how can we feed in these observations? If we just had a gridded data, it'd be very easy for a machine learning model or a numerical model to just make a forecast. But actually, that's not the case. We have lots and lots of different sources, all with their own errors, all showing us different things. So this is what makes one of the things that makes this problem complex. And then what we say at ECMWF is we have an Earth system approach. So we're not just trying to measure, we're not just trying to predict rain, let's say, on its own. We have to predict precipitation, evaporation, this water cycle, this couplings between sea and ice, land, atmosphere coupling. There's lots and lots of complicated intertwined processes that are going on that we need to be able to simulate. And this is, our Earth system approach, and it's a very complex system, as I'm sure you can imagine. So how do we do numerical weather prediction then? So we start with observations, as I said. So this is the observations that you just saw, all these different sources of observation. But like I say, we can't just feed that straight into a numerical model or a machine learning model. So we do something called data assimilation, which is basically kind of what it says on the tin. We're trying to simulate this observational data into a state which we call our best guess of the current state of the atmosphere. And we sometimes call it analysis, so you'll hear me refer to it as that. But basically what it is we take, let's say we take our forecast for today from yesterday, let's say. So that's our previous forecast. But now we have the observation, so now we know what it actually looks like. And so we correct the forecast based on these observations. This is quite a complex mathematical process involving taking gradients and sort of running the model in backwards mode and things like that. So this actually at the moment, in terms of our weather forecast, this takes about half of the computational time of running our weather forecast. Then you have the actual, bit that most people probably think about when they think about weather forecasts, which is the solving of these physical equations. So these equations actually, we don't know if they do or do not have a solution. So this is a very fundamental mathematical problem, which you can win $1 million if you can show whether it has a solution or it doesn't have a solution. So obviously we don't actually solve these equations explicitly, but we have numerical methods which solve them, or machine learning methods, which is what I'll come on to. And then the final bit is this post-processing. So obviously, when you get your weather forecast, you don't just get like a gridded data with temperature and you have to interpret it. No, you get out like those nice little clouds or sun or those sort of images. So that's all part of the post-processing and dissemination. So those are the 4 stages of numerical weather prediction. And where machine learning is coming in is actually not in the, for the moment, it's not in the data assimilation part. It's not in the it's a little bit in the post-processing part, but it's mainly coming in these trying to emulate these equations. So the actual forecasting part. And so this is the next part. So now we talk about maybe the sort of the part that's more interesting to the group. So why is machine learning well suited for weather prediction? Well, as I'm sure you've all experienced, the weather forecast is often wrong. I mean, it's more right than it's wrong, but obviously you only remember the times that it's wrong. And so it's difficult. And as I said, it's all very highly coupled, it's chaotic. So it's very difficult to predict. We also don't really understand a lot of the physical processes. It's still very much an area of research trying to understand how clouds, cloud formations and things like that. And also we're highly limited by resolution, because the problem with the weather forecast is, okay, I could run a very, very computationally heavy model, but if it takes longer to produce me an output, let's say it takes 10 days to produce this output, well, that's too late. I don't need the forecast if it takes me 10 days to produce a forecast for tomorrow, I already know what the weather looked like tomorrow because I only got it 9 days afterwards. So we have very strong computational cost limitations in the world of weather forecasting. And that means that we're severely limited in the sort of resolution that we can have in our models. And that means that it's difficult to represent lots of important processes. So to give you an idea, our current global model is at 9 kilometer resolution, but there's lots of processes that happen at sub 9 kilometers. And but as I mentioned, I mean, we said we had 800 million daily observations, right? there is a huge number of observations, but there's also a huge amount of model data on which you can train machine learning models. And that's what makes this field very, very attractive to machine learning practitioners. So specifically, all the models I'm going to show you now, and basically all the big global machine learning weather models, are actually trained on something which we call the reanalysis dataset, which is specifically ERA 5. And so what reanalysis does is it's just like that data assimilation that I was saying. So it takes observations and it tries to take these observations and fill them in to predict that, not to predict, sorry, to have our best guess of what the weather looked like at that point in time. So there's no temporal aspect. It's just a sort of like spatial infilling. But why we call it a reanalysis is this is like a big project that has been done, which is you take observations. We have observations going all the way back to 1940, but we use our current model to get the best state of the atmosphere in 1940, for example. So these are much better. This is obviously a much better model than anything we had in 1940. But the other thing that it means is you have a consistent model. So that's very important for a machine learning problem. So if we were just to train on the operational forecast, or the operational forecast changes all the time. So every year we have a big upgrade. And so it's difficult for machine learning model to cope if there's an upgrade because the errors change in different ways. But here what we have is basically a weather forecast, well, our best estimate is the way to say it, the best estimate of the weather from 1940 all the way out to present day with one model. So the errors should be consistent across. So what I mean is if we always slightly underpredict the temperature in Antarctica, let's say in the winter, that should be true in the whole data set from 1940 to the present day. And so that's what makes this so attractive to machine learning models. So I want to really emphasize in this talk also the rapid progress in this field. So I've put in various places, I put dates in which things happened. So there was an earlier paper in 2018, which looked at trying to apply machine learning to weather. But really the paper that started a lot of this work was this weather bench paper, which was submitted in 2020. So this is a benchmark data set. And so the true data is the ERA 5, a very coarse resolution, so 6-degree resolution, which is about 600-kilometer resolution. So much coarser than our 9-kilometer operational model. And the training data set is from 1979 to 2015. And the reason that is because I said that it's a consistent model all the way from 1940, but actually 1979 is when we started absorbing satellite data. So we know 1979, the model gets, the observations get a lot better. And so our best guess of the atmosphere also gets a lot better. So most of these models are actually only trained from 1979, but we're still talking about 45 years of hourly data of weather forecasting to train on your model on. So yeah, the training data set is 1979 to 2015. We have a 1 year validation and 2 years of test. And you can play with this. There's the whole point of this was to create a tool which people could use and compare the different methods, machine learning methods on. So they also established some baselines with WeatherBench as well, and a lot of these baselines were used had been used in numerical weather forecasting for a while. So you have the simple baseline, which is you just say today's weather is tomorrow's forecast. So that's the persistence forecast. Then you have the climatology, which is just the average conditions over the last 40 years, let's say. So you just say the weather in the last 40 years, we take the average, and that's our forecast for tomorrow, for example. Then in WeatherBench, they also put in some other baselines which came from the numerical models. So the first came from the operational model, ECMWF's IFS, and also lower resolution versions of the IFS to make a sort of fairer comparison, because the WeatherBench data that they were considering was 5.6 degrees. So again, it's like 560 kilometers. So it's not really fair to try and compare it to the 9-kilometer model. So we also have some lower resolution, and then just some very simple machine learning baselines with linear regression and simple neural networks. And what they were trying to predict was TO50 is temperature basically at the surface. Z500, it's geopotential, but it's not really important. It's the variable that you see storms and things like this. So these are our two headline variables. And what you can very clearly see here is the purple line is the operational model. The blue line is a coarser version. The blue and green lines are coarser versions of the operational model. And then the machine learning model, there's a convolutional neural network here, which is the red line. And you've also got the linear regression, the orange line. Basically, the machine learning models are, well, at short forecast times, they're beating persistence and the climatology, but they're well worse than the operational models, even the coarser versions of the operational models. So this is interesting. This result in 2020, it was interesting. People had started working on it, but suddenly there was no threat to operational, to the numerical models at all at this point. So progress, so that was, this weather bench data set was released and progress was made over the years. So you have, here is, if you go on their GitHub page, this is the leaderboard. So the operational model, you have this Venturi paper in 2020, which, you know, this scores the errors are sort of twice the size in some metrics of the operational model, but it's still getting closer. And then you have some other contributions. So this one is my paper, so I have to point it out. And there's also a UNet approach by Jonathan Wayne, which was quite significant as well. And you can see that they're starting to train. So Jonathan's model is at 2 degrees. So that's 2 degrees. So these are latitudinal and longitudinal degrees, I should say. So, but 2 degrees is 220 kilometers roughly. So, you know, work is slowly progressing in 2020, 2021. And then at the beginning of 2022, in sort of January, I think, Ryan Keisler released a paper using graph neural networks. And what you can see on the right here is, so it was beating quite significantly the previous machine learning models, so the Venturi model and the Wayne et al. Model. And he was sort of approaching the operational scores. So if we just look at this comparison, at 3 days here, it's something like 180. It looks like the operational model is 154, but it's certainly starting to be of the same order of magnitude using these graph neural networks. And what's particularly significant of Ryan Keisler's work is that he did this all on his own. He used a 1 GPU, I think it's all in his paper. And he says, in fact, he tells you how much money it cost him because he bought resources off Amazon, I think, or he paid for resources off Amazon. And so I think it's something like $2,000 or something like that to train a machine learning model that was sort of approaching the operational scores. So this was quite impressive. And he also took the model to 1 degree. So now we're talking about 100-kilometer resolutions.
On that said, Marianne, we invited him to give us a talk at the beginning of November. So it's gonna tell us more about that.
Oh yeah, he's really cool. I mean, it's amazing what he managed to achieve on his own. This is like a single author paper. So yeah, and the basis of a lot of the work that's been done since then. So the other thing that machine learning, there was 2 things of machine learning models that were open questions certainly in 2020 and 2021, and they sort of been answered now, kind of. The first is, how do you want to do these predictions? So in a lot of the approaches on the original weather bench leaderboard, if you wanted a 5-day forecast, you took the forecast at 0 days and you tried to predict 5 days ahead. And that works okay. But it means that, you know, if you are interested in 6 days or 7 days, then you have to retrain your model with 6 and 7 days. And also there's sort of indications that the accuracy is also not as good. The other approach is an iterative approach, which is you train 6 hours ahead, and then you use that 6-hour prediction to initialize your next prediction, 6, 12, 18, 24, etc. And so since sort of last year, definitely, the direct prediction approach is kind of dead. Everyone does iterative predictions. And this is the approach that people take. The other question is whether it's data-driven or physics-guided. Here, all of the approaches I'm going to show you today are data-driven. So a physics-guided approach would be you would have a physical loss metric in your loss metric too. Yeah, so far everyone has taken the data-driven approach because it seems like we don't need physical constraints. However, if we go out to longer forecasts, sort of like climate modeling or sub-seasonal forecasting, then we might need to reconsider this. But for the moment, these 2 questions, iterative and purely data-driven, seems to be the way to go. So this approach, progress, this is a slide that I stole from NVIDIA, just to show you how quickly progress started occurring, basically. So you have Weatherbench, which I mentioned, Wayne, two of the Wayne papers, the Ryan Keisler paper from 2022. And then in February 2022, NVIDIA came out with ForecastNet, and it was the first to be trained at the full resolution of the Era 5 data, so at 0.25 degrees. And this was very impressive to go, if you think just basically the year before, or the year and a half before, the state of the art was 2 degrees. So to go all the way to 0.25, I mean, NVIDIA have all the GPUs. So that's part of the reason why they could make this progress. But once they made this progress, everybody followed, basically. So ForecastNet, just a little bit about their architecture, what they're using. So it's sort of like a little bit of a transformer approach, but also combined with an adaptive Fourier neural operator. So what does this mean? So they take their inputs, they take patches, and they use an embedding. But then they also do a Fourier transform to convert this into spectral space. And this paper got people kind of excited in the weather community because, for example, it's similar to what we do in the numerical model, which is that we don't actually run our model in normal space, in the latitude and longitude. We actually run the model in spectral space. So this idea of going to spectral space was very interesting, and people were very sat up a little bit when they showed this. The other thing that's significant is that I can't remember quite off the top of my head, but I think Ryan Keisler, there was definitely a restricted number of variables that he was predicting, but ForecastNet was predicted quite a large variety of different weather variables, and that's what you need for a weather system. A weather system that only predicts 2 or 3 variables is not very useful. A weather forecasting system, sorry, which only predicts a few variables is not very useful. The next big one was Pangu weather, which came out in November of 2022, so the November of last year, which is it's a transformer approach. So it's a simpler transformer approach, really. And here you have an embedding, a patch embedding, fed into the encoder and then the decoder, and then you split it back up to do the forecasting. So what's significant about Pangu weather? So they also trained on 0.25 degree resolution, so that's 28 kilometers. But ForecastNet, the NVIDIA version, needs 160 GPUs to train. And just for context, I mean, here at ECMWF, we have 64 GPUs. We can't even, we don't have half the resources that NVIDIA used to train their model. With Pangu, it's still a computationally heavy model, but it's much more reasonable. So it needs a lot less GPUs to train. And then we have this paper, which came out, which was submitted to arXiv on the 24th of December and ruined quite a few people's Christmases, I think. I mean, a lot of people read this paper over Christmas. And this is Graph Class by DeepMind. And this is a graph neural network approach. So it's similar to what Ryan Keisler was doing, but sort of a bit like Ryan Keisler's approach on steroids. And there are a couple of significant things about this approach. Is firstly, it only has 18 million parameters to train. So in terms of how much computational resource you need to train, relatively speaking, it's very cheap, or relative certainly to ForecastNet and NVIDIA's model. And the way it works is you have your input weather state. Again, you have an encoder, and this encoding is passed on to this processor, then decoded, and then going back into the forecast, the predicted state. And like all of these models are using this iterative, here they called it rolling out the forecast, but it's this iterative 6-hour step approach. But the really key thing of the graph neural network is this multi-mesh message passing that's going on. So in the processor, you have simultaneously a very coarse grid, and then you go progressively finer, and you have message passing between the nodes, and the message and you have on the nodes and on the edges, all you have is linear MLPs. And so that's what makes it so cheap. That's what means that the parameter, there's really not many unknowns to train on. really the key part of the neural network of the graph neural network in this approach is the message passing structure. And yeah, we found that the multi-mesh approach also really helps them as well. And so this was really the headline figure of this paper that made ECMWF sit up, basically. So those of us who are working machine learning, so before I was doing machine learning here, but in a sort of a more of a, not on this scale, and this paper really made people sit up and say, okay, wait a minute, we need to do something. And the reason was this plot here, this figure here. So this is a scorecard like the scorecards that we would produce here with the variables that GraphCast predicts. So these are basically, the numbers are indicating the different levels of the atmosphere. Then you have the variables, this geopotential that I mentioned before. And you have temperature, wind speeds, U and V, humidity, and then some surface variables of 2-meter temperature and mean sea level pressure. And where it's blue, that means that, so firstly, this was really impressive how many variables they forecast. This is really like an operational atmospheric weather system. But also what's really significant is where it's blue, that means that their root mean squared error is better than the ECMWF model. And where it's red, that means the ECMWF model is better. And so what you can see is GraphCast has some issues in the upper atmosphere, but that's because of the way they chose to weight their loss function. So they chose to disregard the upper atmosphere in order to get better scores in the lower, in the sort of nearer the surface, which is obviously generally where we tend to care more about the weather. And so really, this is very impressive. Now, the caveat of this, like with a lot of machine learning problems, it's just like machine learning and weather, is root mean squared error actually the best metric? So we use root mean squared error to assess our forecast, but we also use lots of other metrics. Yeah, so just beating on root mean squared error is not sufficient, but it's certainly an amazing first step. So I wouldn't want to conclude from this that GraphCast is better than our model, than the numerical model. What you should conclude is that it's certainly competitive with the numerical model. And then, so I said, oh, we've explored this. So actually, this is hot off the press. So over the last couple of months, we've been working on our own machine learning model. And we sort of released it to the public, if you like, on the 13th of October, so last Friday the 13th. It is based on, it's called AIFS, and it's not using GraphCast's code, but it's based on this idea of the graph neural network with the message passing and the processes. So in some ways, it's quite similar. It's certainly inspired by GraphCast. And IFS here, this is our numerical model, and AIFS is our machine learning model. And you can see that AIFS on this metric, which is root mean squared error for geopotential, on this metric, our AIFS is performing better than IFS. But what I actually wanted to show you, because I think it's really cool, is now we have in-house, we are running all of these machine learning models. It's not operational in the sense that we call it in these versions experimental. We're not saying you should base any sort of critical decisions on this, but you can get real-time forecasts for the machine learning models. And it's available here on this charts website. So I try and if you just go to charts.ecmwf.int. So this has always existed. So this is where you can check out our numerical weather model and see the forecast. But what you can also do now is you can look at the experimental machine learning models. And so you can see AIFS, ForecastNet, GraphCast, and Pangu. And so this is all being run on our machines. So we have sort of collaborations is probably too strong a word, but we've spoken to them. They've given us their inference code and their weights. And so we are making these predictions. We're making forecasts with their machine learning model. And so you can see, for example, AIFS, which is R1. This is the mean sea level pressure and the wind speed. So this is forecast for 6 hours, but we can also forecast it out to 144 hours, which I don't know, 6 days, I think. And we go all the way out to 10 days. And you can compare and contrast with any of these models. So ForecastNet, you can do the same, and you can see how different it is. So what I should say also about AIFS is that currently our model is only trained on 1 degree data. because we're still sort of exploring and developing, whereas ForecastNet and other models are trained on 0.25 degree data. So they will be naturally a little bit better than ours. But you can also compare those scorecards like I just showed you. We have on this website as well, the scores of the forecasts. So here we go. Oh, sorry, this is AIFS against. But here we go. So you can see how for this Z500, how it's performing against the other machine learning models. And so we are basically at the same accuracy as GraphCast. And ForecastNet and Pangu are all worse than GraphCast and AIFS in this metric. So this is why we think graph neural networks are the way to go, basically. But here you can also play around with other metrics. So we also look at things like called anomaly correlation. So here, the larger the number, the better. And so you can see again that GraphCast and AIFS are they sort of stick together. They're doing better. They're doing better than the other machine learning models in this metric. So this is really cool, and anyone can explore this. This is available. I'm not logged in. So if you're logged in at ECMWF, you can get a few more charts, but now, as of last Friday, anybody can see any of this. So it's really cool. And we have this as a screenshot I took from our blog. So we have a blog where we're going to be talking about the development of our model as we go along, basically. So is that it then? Do we just stop? Is that it for machine learning models? Sorry, for numerical models? Well, that's not quite the case just yet. There are lots of challenges still to come. So I'm going to address some of the challenges here and talk about what we're doing to try and address them. So the first challenge is this thing of training towards root mean squared error. So this is taken from Ryan Keisler's paper, and he shows that in his case, training on root mean squared error results in a smoother forecast where you're losing the fine detail. So that's a bit disappointing because you obviously want to know very precise spatial details. Otherwise, we would just stick to a very, like a 2-degree model, for example. So this is what the thinking was at the beginning of 2022, that these forecasts would be far too smooth to be really any use. Since then, we have done our own analysis. So we have submitted, and it should be shortly published, a paper where we have looked at Pangu model, the Pangu model. So that's the 3D transformer, and tried to assess it using the metrics that we would normally use to assess our own numerical forecast. And here we have an example of an extreme cold event. The right-hand side, these two images of the top right is the 2-day forecast of our operational model, the 6-day forecast of our operational model compared to Pangu day 2 and day 6. And you can see it does look a little bit smoother. Part of that is because Pangu is at 0.25 degree resolution, which is 28 kilometers instead of the 9, but it's certainly managing to capture lots of little subscale features. So we don't see as much of the smoothing as what Ryan Keisler appeared in his paper at the beginning of 2022. The other metric we have here, which is activity. So I accidentally cropped off the legend, I just realized, but basically activity means the higher the activity, the less smooth the forecast. And the blue line is Pangu, the red line is IFS, the black line is ERA5, so what Pangu was trained on. And you can see it's all sort of the same order of magnitude of smoothness. And the pink line is a forecast that we know is smooth. And so you can see that, okay, a known smooth forecast, the activity is much, much lower than the activity that you're getting out of Pangu, for example. So yes, maybe smoothness is an issue, but it's not as big an issue as we feared. Excuse me. The other big issue is training on observations. So far, all machine learning models are only trying to replace the forecasting part. But as I mentioned, 50% of the computational time in the numerical model comes from using the numerical model to assimilate the observations. So it's difficult for machine learning to replace the data assimilation part, because you have lots and lots and lots of different sources of information, and also the information isn't coming in on a nice grid. You're getting lots and lots of different sources, and these, for example, a source from a plane will move around and things like that. So it's a very, very, very difficult problem, and we don't have ideas just yet about what to do, but I'm sure people are working on it. So for the moment, we're still training on analysis, but actually, yeah, this means that we shouldn't really call these machine learning weather forecasts purely data-driven, because they're actually relying on the data assimilation on the numerical part for now. Then the next issue, the next issue, which is perhaps the most important, or one of the most important, is how do you add uncertainty into machine learning models? So weather forecasting is inherently uncertain, and that's because of the chaotic nature of the Earth system, also the uncertainty in the input conditions and the uncertainty in the model that you're running. And it's very important to quantify this uncertainty, specifically in the case of, let's say, extreme events. You likely you need to know if there's a probability of some extreme event happening, even if it's a small probability. But you also need to quantify, as you go out to forecasts of longer forecast times, you get more and more uncertainty. And so really at long forecast times, a single deterministic forecast is not that useful because it's very likely to be wrong. So what you need is a range of possible forecast scenarios, basically. And so that's what we have in numerical modeling. That's what we have. We have an ensemble of models with perturbed initial conditions and perturbations in the model itself. And what we hope is that the sort of perfect distribution would be one where which is wide enough that the actual event is captured, but not so wide that it's sort of irrelevant. You know, you have equal likelihood of lots of different events happening. That's also not very useful. And so this is a big question. In order for machine learning models to actually be a useful weather forecasting system, we need uncertainty. And this is actually what I'm working on at the moment. So trying to build uncertainty into AIFS. We have some, preliminary ideas. None of these are particularly revolutionary. But one of the things that we could try is using ensemble initial conditions. So I said, you know, one of the ways that we add uncertainty into the numerical models, we just perturb the initial conditions. But we can also perturb the initial conditions, which we use to initialize the machine learning model as well. So that's an easy first step. Another sort of, this is really a baseline approach as well, is that obviously if you change the seed in your training at the beginning, you can use the ill-posed nature of the problem to find different quasi-optimum solutions. And so you can use that then to build a multi-model ensemble. So that's one approach. It's very simple, really, multi-model approach. The other thing is that we can train, instead of training to minimize root mean squared error, we can train to minimize some sort of probabilistic approach to some sort of distribution. So yeah, well, we know what the distribution should look like, and we can train to match that distribution. And then the final approach, which may be the most interesting, is using a generative model approach trained on real samples to generate new samples. So generative adversarial networks are particularly promising because they could encourage physical realism. And this is something that we're all targeting, physical realism, but in the end, maybe we might also get hallucinations. And so our current approach to this is we're not just, you know, we've got all these ideas. We don't just want to select an approach based on theoretical explanations, but we want to instead make decisions based on results. So we want, and also you can combine a lot of these approaches, right? They're not independent approaches. But yeah, the question is still very much out there. What should we do? Then the last challenge that I want to address, but I think is one of the most important, is how can you build trust in machine learning models? So every Friday afternoon here, we have what we call the weather discussion, where we look at the forecast for the last week, and we see when there were big errors, which we call the forecast bust, and we try and understand why these happened, and how we can fix the model. And really, the black box nature of machine learning models means that this is very difficult to do, and so it makes it difficult to build trust in them. And this is sort of comes on the second part of the slide, which is how do you evaluate the machine learning solution? So how can you query the model? How can you understand it? How can you be sure that it's producing the right thing for the right reasons? So one way is incorporating physical knowledge into machine learning models, either by using physical constraints or other things as well. But you can also try and evaluate the machine learning solution by looking at specific use cases, testing physical reasoning, benchmarking on existing solutions, And so basically then that would be similar to what we do in the weather discussion at the moment. But obviously explainable AI could also be used here. And this is something that I'm very, very keen to try, but explainable AI is difficult with such a complex model and such a complex system. It'll be interesting to see how much information we can actually get out, but yeah, it's certainly something that we want to look at. But just to give you an example of the evaluating whether it produces correct physics, so here we have 5 simulations. So this was taken from the ECMWF newsletter. So this is Storm Eunice over the UK. So on the top left, we have the analysis, so our best guess of what actually happened. Then we have the operational forecast, and then we have 3 machine learning models. And what you can see is ForecastNet is definitely worse. Pangu weather is starting to approach, yeah, it's doing a bit better. But I think, I mean, it's obviously debatable when you're just looking at it, but I think that GraphCast is out of the machine learning models is doing the best job of representing the true state. It's doing quite a good job here, specifically in this sort of red region, I think. But HRES is still doing better, so our operational model is still doing a better job than GraphCast, I would say, for this particular event. But a lot of that is also coming, so it's got, and I say that because it's got more of this sort of spatial resolution, these features that really you can really sort of see how the system's evolving, but part of that is, as I keep on saying, to do with the resolution issue. So HRES is just 2 or 3 times more higher resolution than GraphCast. And so with that, I reach my conclusion. And actually, what I'm actually going to do is bring you back right to the beginning of the presentation, where I said, could deep learning methods replace numerical weather models? And the answer is, I don't know. But it's evolving very rapidly, and it's really looking very, very interesting. And you saw the pace really from the Pangu weather paper was submitted in November of last year, and we are 1 year later. ECMWF has an AI model that we've developed in-house, so it's really, really very, very quick. And who knows in the next year what's going to happen. And then my final slide is just a little plug. So this is something we did back in January. But it's still available online. So it's a massive open online course in machine learning and weather and climate. So the idea is to teach weather and climate to machine learners and to teach a bit of machine learning to weather and climate people. It's freely available to anybody anywhere on the globe. I gave a webinar with actually one of the people from NVIDIA and one of the people from DeepMind, and we all had very bad takes about what we thought was going to happen, what was going to happen in this field in 5 years' time. I think we were proven wrong within about a month. So it just moves so quickly. But so maybe the webinars are interesting to watch in hindsight, but certainly the course material is still very relevant. And so with that, I'd like to thank you and open the floor to any questions.
Thanks a lot. That was a great talk. It was a really great talk. I'm very happy that there is also material available for new students for us to look at it. And so, do you guys have any questions?
Thanks, Mariana. That was a really interesting talk. Just a question about the direct versus iterative process that you were speaking about. Like one of the obvious things that sort of came to my mind when I was thinking about the iterative process was like, if you have errors which sort of crop up early on, you sort of propagate those errors more and more, and they sort of build in amplitude. How do you deal with that, basically?
Yeah, that's a really good question, and I sort of glossed over it a little bit. That's a very good question, because we do actually look into it, but it's not as important as you would think, these errors that propagate through. But what we actually do is we follow in AIFS, if I speak about that, and we follow GraphCast. And what we do is we minimize the error not only on the 6 hour, but we do it out to 72 hours, which is 3 days, which I guess is 12 steps. So yeah, so we're trying to minimize the error, not just at step 1, but at step 2, step 3, step 4, etc. And we find that that's enough to get a good forecast out to 10 days. However, if you then take that forecast and you go out to 20, 30 days, the errors, just like you say, the errors start propagating and coming back in again if you don't constrain it properly. So if we wanted to do longer range forecasts, then we would have to probably do this error verification, not just up to 72 hours, but maybe all the way out to 240. We don't know yet. But yeah, you have to be very careful how the errors propagate through.
Was that the reason why the error was lower after 10 days compared to in the AI model compared to
it should, which one was that? Sorry, let me see if I can.
So there was a plot of a forecasting window, and it should, yes, this one.
Ah, okay. So you're saying
why is the error lower? If I interpret the plot correctly, why is it lower after 10 days forecasting?
as in why is the difference bigger, or?
Yes, what do I like the error of the AI model is lower compared to the numerical model?
Yeah, so it's lower
Right,
the whole
so
way
what-
through.
Yes.
Yeah. So yeah, I mean, one thing also is at 10 days, you're definitely going to start seeing a little bit more of smoothing in the AIFS model or any of these AI models, and so that results in a smaller root mean squared error. So that's a little bit why it increases. But yeah, it's not. If we then to take this graph out to 20 days, you would see that it would then start the error from AIFS would probably start getting worse than the error from IFS. But yeah, it's difficult. And 10 days is sort of an arbitrary cutoff period, but it's what all these machine learning companies were using, and so that's why we used it as well for now for our results.
Hi. I was just wondering if you can just say a bit more about your machine learning module in terms of like the decisions that you had to make, any lessons learned along the way.
Yeah, so basically our machine learning model, if I just move slides, looks very much like this one. So for the moment, we sort of have followed GraphCast. So they had their very nice paper, and so we could see that we coded it. We saw that they were using this graph neural network approach, and so we coded it up in Torch and Torch Lightning. And we tried to follow their approach. So one of the things that maybe we might tweak later on is, so they have these multi-meshes, and they go out to 6 levels. But maybe we could go out to more levels. We could get even finer resolution, let's say 7, 8, 9 levels. But then that comes at a computational cost. So really, that's one of the big decisions that you've got to make in your processor. How many of these multi-meshes are you going to have? Because the advantage, obviously, is if you have a very fine mesh, then that's great, because then you can then you can really capture the small scale things that are going on. But if you have very coarse meshes, then it's cheaper. So that's one of the decisions that you have to make. Then also, I was saying that we have these linear MLPs on the nodes and the edges. Well, I think I can't remember quite off the top of my head, but I think for now it's just exactly what GraphCast used in their paper. But we could obviously play with that and tweak with that, and put more linear layers in the MLPs, or we could maybe not use MLPs. But I think in graph neural networks, people generally do use just MLPs, and it works very well. So that's a couple of the things that we had to think about, and also, something that we might play around with later is exactly what do these meshes look like, these nodes and these edges. I mean, this is not that different if you've got a numerical modeling background. This is not very different to what a mesh and a numerical model might look like. So there's stuff that we can learn from that. So yeah, these are the sorts of decisions that you're already thinking about.
Thank you.
And a node here, what does it represent? Does it represent multiple? It's like a heterogeneous graph, so
it's a homogeneous graph. But so a node is really just a point, if you like. So you can even think about it. so it's not a point in latitude longitude. If it was in the encoder, it is, but then it gets encoded into a latent space. So it's just a point in the latent space, which is connected to other points in the latent space by edges. And so, the difference, the reason why we have these multi-meshes is that when you have more of these nodes in the latent space, then you can encode more of the information from the original grid, let's say, from the original latitude longitude grid. And so it's almost like you're giving yourself more degrees of freedom, basically, the more nodes you have. So it's not, it's a little bit misleading in that the nodes in the latent space are not representative of spatial features. But more degrees of freedom, I would look at it that way.
So the different meshes, they do not only represent different resolution, but also added level of added information.
Yeah, exactly. Yeah.
Other questions online, maybe? People in the room.
I have a question actually. So in terms of the iterative method, how do you optimize for the time step? Do you just do exactly what GraphCast did?
So we do, so in GraphCast they optimize first. I'm not sure exactly what they do, how they do it, but what we do is we first optimize for the first 6 hours, and then when we're happy with the first 6 hour jump, basically, then we optimize out to 72 hours. And GraphCast definitely do that. They optimize out to 72 hours. I don't know if they do the 6 hours training first. I guess they do, because that's what makes most sense. The 6 hours is kind of arbitrary. 6 hours is just a nice temporal resolution, but Pangu actually experimented with this. They train to 24 hours. They do 24-hour time jumps. They also do 12-hour time jumps and 6-hour time jumps. And then if they want a forecast, let's say for 36 hours, they do one prediction of 24 and one prediction of 36. One prediction of 12, and that gets them to 36. So this is what they call their hierarchical temporal time stepping. Sorry. And so, for the moment, we're just doing the predicting out to 6 hours, and then at a later stage, basically fine-tuning on these rollout.
So, well, if there are no other questions, then I will thank you a lot. It was a really great talk. It was very inspiring. Left a lot of ideas for the weekend. And then I guess if people have questions, or they can probably reach out to you.
Sounds good. Thank you for inviting me. And I'm always happy to answer any questions. And I think watch this space, really. I think there's going to be a lot coming out soon. Who knows what will be in 1 year's time? This whole presentation will be completely irrelevant. So
there might be something coming up this evening which is gonna ruin our weekend. So
exactly.
Okay, well, have a nice weekend then, and
You
thanks
too.
a lot.
Thank you.
Okay,
Bye.
thank you. Bye.
Thank you.